ever imagine like tossing your old bulletproof vest in the microwave
Okay.
and getting back like the stuff to make a brand new one?
Oh, wow.
It's not as sci-fi as it sounds.
Really?
We're diving deep into the world of Aramid fibers today.
Okay.
You know, the super strong polymers and everything, like from protective gear to airplanes. And there's this groundbreaking research could reshape the entire industry. It uses, wait for it,
Okay.
microwaves.
Wow, that's pretty remarkable.
Right.
Talking about Kevlar,
Oh, yeah.
Twaron, known for their strength, durability. But the downside to that, always been recycling them.
Yeah.
Effectively.
Because we know they're valuable.
Right.
But those traditional recycling methods, not ideal.
No.
You end up with like lower quality fibers.
Exactly.
Or you need all those harsh chemicals
Yeah.
and high temperatures to break them down.
Mechanical recycling compromises the strength. And conventional chemical recycling, energy intensive, creates hazardous waste.
Totally.
So that's why this new research out of the University of Groningen and NHL Stenden, such a game changer.
Yeah.
They found a way to use microwave energy to depolymerize aramids.
And what's that like in simple terms?
Essentially reversing the manufacturing process.
Oh, wow.
You recover those building blocks much cleaner way, faster, more efficient.
This depolymerization thing, this is where it gets interesting for me.
Oh, how so?
Instead of just like shredding or melting, we're breaking them down at the molecular level.
Precisely. Like disassembling a Lego structure.
Oh, I like that.
Carefully back into the individual bricks.
Yeah.
And the beauty of the microwave method, it allows us to target specific bonds in the polymer chain. So we can control the types of monomers.
Monomers.
Yeah, those individual building blocks that we recover.
So it's not just breaking things down. It's about reclaiming those high-quality building blocks so we can create brand new aramid fibers, like giving these materials a second life.
And potentially a third, fourth, or even more.
Wow.
That's the real power of this technology.
Yeah.
The potential to move us towards a truly closed-loop system for aramid fibers, drastically reducing waste. Our reliance on virgin resources.
It's kind of wild, right?
It is.
That something as simple as a microwave
I know.
could revolutionize a whole industry, and they're achieving a 96% conversion rate.
Yes.
In just 15 minutes.
Incredibly fast and efficient.
That's unheard of, right?
Traditional methods take hours, even days, to achieve a similar level of depolymerization.
And you said it doesn't require those harsh solvents either.
Right, because the microwave method operates at lower temperatures.
Okay.
And doesn't require those harsh solvents.
Yeah.
It's also much more environmentally friendly.
So it's a win-win.
Yes.
For the industry and the planet.
A potential win-win.
Okay, but let's be realistic here.
Sure.
Scaling up any new technology comes with challenges.
Of course.
How feasible is it to actually implement this?
That's a great question.
Yeah.
And of course there are hurdles.
Yeah.
This research is still early. And there's a lot of work to be done in terms of optimizing the process and developing the infrastructure needed for large-scale implementation. Yeah. But the potential is there.
Okay.
And the researchers are already collaborating with Tijan Aramid.
And who are they?
A leading aramid fiber manufacturer.
Oh, okay.
To explore those next steps.
So they're not just like stuck in a lab. Oh, yeah. They're actually looking at how to make this real.
Right.
That's exciting.
It is.
But I'm also wondering about the energy requirements of this microwave method.
Right.
Could we end up like offsetting the environmental benefits?
Yeah.
By consuming large amounts of energy?
That's a valid concern.
Yeah.
And it's something the researchers are actively investigating.
Okay.
Remember, this method already operates at lower temperatures than traditional approaches.
Right.
Which is a good starting point.
Yeah.
And there's ongoing research into optimizing the microwave reactors.
Okay.
For even greater energy efficiency.
So there's still work to do.
Yes.
But the early results are really promising.
They are.
What are some of the potential implications of this?
Yeah.
Beyond just recycling bulletproof vests?
That's where it gets really interesting. This technology has the potential to be applied to other types of hard-to-recycle polymers.
Like what? Give me some examples.
Well, certain types of plastics immediately come to mind.
Yeah.
Imagine being able to take those mountains of plastic waste and instead of just downcycling them into lower-grade materials, actually depolymerize them back into their original building blocks.
Wow.
We could create a closed-loop system for plastics, significantly reducing our reliance on fossil fuels and mitigating the environmental impact of plastic pollution.
And what about those composite materials you mentioned earlier?
Right, the ones that are notoriously difficult to recycle.
Because they combine different types of materials.
That's another area where this technology could be transformative. If we can figure out how to selectively depolymerize specific polymers within a composite material. We could potentially separate and recover those valuable components.
And what would that allow us to recycle?
This would open up possibilities for recycling everything.
Wow.
From car parts, wind turbine blades, to electronic waste.
Wow.
Construction materials.
It's almost too good to be true.
It is pretty remarkable.
Are there any potential downsides?
Well, of course.
Yeah.
Every new technology comes with challenges. One of the key hurdles will be adapting the microwave technology to work with different types of polymers. Each polymer has its own unique chemical structure.
Right.
So the depolymerization process will need to be carefully tailored to target the specific bonds within those structures.
So it's not a one-size-fits-all solution.
No, it's not.
It sounds like there's still a lot of research development needed to fine-tune this for different applications.
Absolutely. Another challenge will be scaling up the process to handle the vast amounts of waste we generate. Building the infrastructure to collect, sort, process these materials on an industrial scale will require significant investment and collaboration. Researchers, manufacturers, policymakers.
And even if we can overcome those like technical and logistical challenges, there's also the economics of it all.
Of course.
Will it be cost effective? To recycle these materials using this new method?
That's a crucial factor. The cost of recycling will need to be competitive with the cost of producing virgin materials. But the potential for cost savings is there. Especially as the technology matures, becomes more efficient.
So it's not just about the science. It's also about the economics. And the logistics of creating a viable system for recycling these materials.
Exactly. And there are broader societal considerations as well.
Like what?
For example, we need to ensure that this technology benefits everyone. And doesn't exacerbate existing inequalities. We need to think about how to create a circular economy that is equitable and inclusive.
That's a really important point.
It is.
It's not enough to just develop new technologies. We also need to consider the social and ethical implications of those technologies.
And ultimately, the success of this technology will depend on whether we can create a system that is both environmentally sustainable and socially responsible.
This has been really insightful.
It has been.
I feel like we've just scratched the surface here of what's possible. With this microwave-assisted depolymerization technology.
It's a testament to human ingenuity, that we're constantly finding new and innovative ways to solve complex challenges. Who knows what other breakthroughs are just around the corner.
Well, before we wrap up, I wanna go back to the Aramid fiber story for a second.
Okay.
You mentioned earlier that the researchers are collaborating with Taiji and Aramid, a major player in the industry.
They are.
What are some of the specific challenges they're facing?
Well, one of the key challenges they're addressing is optimizing the depolymerization process.
Okay.
For different types of Aramid fibers.
Right, because there's not just one type.
No. Each type of fiber has its own unique composition and properties.
Yeah.
So the reaction conditions need to be carefully adjusted to ensure efficient breakdown and recovery of the monomers.
So it's not just about finding the right microwave settings. It's about understanding each material.
Yes.
And tailoring the process.
Precisely.
Yeah.
Another challenge is developing efficient and cost-effective methods for purifying the recovered monomers.
Okay, and why is that so important?
Remember, the goal is to produce monomers that are comparable in quality to virgin materials.
Right.
So the purification process is crucial.
So it's not just about breaking down the polymers.
Yeah.
It's about refining them.
Yes.
So they can be used to create those high-quality new materials.
Exactly. And then there's the challenge of integrating this new technology into existing manufacturing processes.
Okay.
Aramid fibers are used in a wide variety of applications, each with its own specific requirements.
Yeah.
So the recycled monomers need to be seamlessly incorporated into those existing workflows.
It's a complex puzzle.
It is.
But it sounds like they're making progress.
They are.
I'm curious to see how this collaboration evolves.
That's am I.
And what kind of impact it has.
It's fascinating to see how research and industry are working together.
Yeah.
To bring these innovations to life. And who knows? Yeah. Maybe one day we'll see a world where Aramid fibers are routinely recycled and reused.
Like we recycle aluminum cans.
Exactly. Just like we recycle aluminum cans and glass bottles today.
That would be remarkable.
It would.
And it would have a ripple effect throughout the whole manufacturing ecosystem.
You would.
But before we get too far ahead of ourselves, let's take a step back.
Okay.
And consider what this all means for the average person.
Yeah.
How might this technology impact our daily lives?
Yeah.
In the years to come. We'll explore that.
We will.
In the final part of our deep dive.
So it really is a fascinating process.
Okay.
Like imagine those long chains of molecules that make up the Aramid polymer.
Like a microscopic super strong chain.
Yes, exactly.
Okay.
And the microwaves act like tiny scissors.
Okay.
Snipping those chains at very specific points.
So it's not random.
No, it's not just about breaking things apart randomly.
Okay.
It's a controlled process.
Okay.
That yields these shorter units called monomers.
So those monomers are like the individual links in the chain.
Yeah, like that.
And by controlling where we make those snips, we can create like different types of monomers.
Exactly.
Each with their own like properties.
Precisely.
Okay.
It's this precision that allows us to produce monomers of exceptionally high quality.
And how are we talking?
Comparable to the virgin materials.
Wow. Okay.
Used in the initial production.
So that's what makes this so different from the traditional methods. It's not just recycling. It's like hitting a reset button, bringing it back to a near pristine state.
Precisely.
And those high-quality monomers, those are key to creating new Aramid fibers, right?
Yes, with that same strength and durability and heat resistance.
So theoretically, we could take like an old bulletproof vest, break it down, and use those monomers to create a brand new one.
Yes.
With like no loss in performance.
Absolutely.
That's huge.
It is.
Especially for industries that really rely on these materials.
Think about aerospace, for example.
Oh, okay.
They could reclaim valuable Aramid materials from old aircraft components.
Okay.
And use those monomers to create new lightweight parts.
For new planes.
For the next generation of airplanes.
Oh, wow.
It's a win for efficiency, cost savings, and sustainability.
Okay, so this technology, it could reshape the Aramid fiber industry.
Yeah.
But you said earlier that it could have implications for other types of polymers too.
That's what makes this research so exciting.
Okay.
While the focus has been on Aramids,
the underlying
principles could potentially be applied to a wide range of polymers that are currently difficult to recycle.
Like what? Give me some examples.
Well, certain types of plastics.
Okay.
Imagine being able to take those mountains of plastic waste.
Yeah.
Instead of downcycling them. Actually depolymerize them.
Back into their original building blocks.
Yeah.
Wow.
We could create a closed-loop system for plastics.
Okay.
Reducing our reliance on fossil fuels.
Right.
And mitigating the impact of plastic pollution.
And what about composite materials?
Yeah.
The ones that are like notoriously hard to recycle.
Right, because they combine different types of materials.
Yeah.
That's another area where this technology could be transformative.
Okay.
If we can figure out how to selectively depolymerize the specific polymers within a composite material, we could separate and recover those components.
And what could we recycle then?
This would open up possibilities for recycling everything.
Wow.
From car parts and wind turbine blades to electronic waste and construction materials.
It almost sounds too good to be true.
Of course, every new technology comes with its own challenges.
Okay, like what?
One of the key hurdles will be adapting this microwave technology to work with different types of polymers.
Right, because each one's different.
Each polymer has its own unique chemical structure.
Okay.
So the depolymerization process needs to be tailored to target the specific bonds.
So it's not a one-size-fits-all solution.
No, it's not.
It sounds like there's still a lot of research and development needed.
Absolutely.
To make this work for everything.
Another challenge will be scaling up the process to handle all the waste that we generate.
Right.
Building the infrastructure to collect and sort and process all these materials.
On a large scale.
Yeah. On an industrial scale, it will require significant investment and collaboration.
Between
researchers, manufacturers, and policymakers.
And even if we can overcome all those challenges, there's still the economics of it.
Right.
Will it be cost effective to actually do this?
That's a crucial factor. The cost of recycling will need to be competitive with the cost of producing virgin materials.
But there is potential there, right?
The potential for cost savings is there, especially as the technology matures and becomes more efficient.
So it's not just about the science. It's about the economics and the logistics, too.
Exactly.
Of actually making this work.
And there are broader societal considerations as well.
Like what?
For example, we need to make sure that this technology benefits everyone.
Right.
And doesn't exacerbate existing inequalities.
Yeah, that's a good point.
We need to create a circular economy that's equitable and inclusive.
That's really important.
It's not enough to just develop new technologies.
Right.
We need to consider the social and ethical implications as well.
I agree. And ultimately, the success of this technology, it hinges on whether we can create a system that is both sustainable and responsible.
I agree.
This has been really insightful. I feel like we've only just scratched the surface.
We have.
Of what's possible with this technology.
It really is a testament to human ingenuity.
Yeah.
That we're finding new and innovative ways to solve these challenges.
Who knows what else is out there?
I know, right?
Well, before we wrap up,
okay,
I want to go back to the Aramid fiber story for a second.
Sure.
You mentioned that the researchers are collaborating with Tijan Aramid.
Yes, they are.
What are some of the challenges they're facing in scaling this up?
One of the key challenges is optimizing that depolymerization process.
Okay.
For all the different types of Aramid fibers.
Right, because there's so many different types.
Each one has its own unique composition and properties.
Okay.
So they have to adjust to the reaction conditions.
You do what?
To ensure efficient breakdown and recovery of the monomers.
So it's not just about finding the right microwave settings. No. It's about understanding each material.
Yes, and tailoring the process.
Okay.
Another challenge is developing those cost-effective methods for purifying the recovered monomers.
Why is that so important?
Remember, the goal is to produce monomers that are comparable in quality.
To the virgin material.
Exactly. Okay. So that purification process is crucial.
So it's not just about breaking things down.
No.
It's about refining those building blocks to create high-quality new materials.
Exactly. And then there's integrating this technology into existing manufacturing processes.
Okay.
Aramid fibers are used in a lot of different applications.
Right.
Each with their own requirements, so those recycled monomers need to be seamlessly incorporated.
It's like a complex puzzle.
It is, but they're making progress.
I'm curious to see how it all evolves.
Me too. It's really interesting to see the research and industry working together to bring these innovations to life. Who knows? Maybe one day we'll see a world where Aramid fibers are routinely recycled.
Like aluminum cans.
Just like aluminum cans and glass bottles today.
That would be amazing.
It would be a remarkable achievement.
And it would have huge impact.
It would have a ripple effect throughout the whole manufacturing ecosystem.
But before we get too far ahead of ourselves, let's take a step back. And consider what this all means for the average person.
Right.
How might this technology impact our daily lives in the years to come? We'll explore that in the final part of our deep dive. It's mind-blowing to think we could be on the verge of a world where recycling, isn't just about tossing things in a bin, but about actually reclaiming and reusing materials at like a molecular level.
Yeah.
What does that future even look like for like the average person?
Imagine a world where products are designed with this kind of closed-loop recycling in mind. From the very start.
So we're talking about like a shift in thinking then.
Yeah, from simply making things durable to making them easily disassembled and their components readily recyclable.
So it's not just about the technology itself. It's about how that technology changes the design and manufacturing process.
Right. We could see a whole new wave of products that are built to be perpetually reborn.
It sounds almost utopian.
It does.
But it makes you wonder about the economic implications. If things are designed to last longer and be easily recycled.
Right.
Wouldn't that disrupt like current consumption patterns?
That's a valid point.
Yeah.
And it's a conversation we need to have as a society.
Yeah.
A truly circular economy would require a shift in our mindset. From a linear model of consumption to a more cyclical one. Where value is extracted from materials over much longer periods of time.
So it challenges like existing business models. And how we think about the things we buy and use.
It would require us to rethink that relationship.
But isn't that ultimately a good thing, though?
I believe so.
Yeah.
Moving away from a culture of disposability and planned obsolescence towards a more sustainable and mindful approach to consumption.
It seems like it would
require us to prioritize quality over quantity.
Yeah.
Durability over trendiness. And to really value those resources that go into making the products we rely on.
And create new opportunities, right?
It would create new opportunities for innovation. And entrepreneurship.
As businesses adapt.
To this new paradigm.
It's fascinating to think about all the ripple effects of this. We started talking about microwaving bulletproof vests.
Right.
And now we're discussing a potential like paradigm shift in our entire economic system.
It's a reminder that scientific advancements rarely exist in isolation. They could disrupt industries, challenge assumptions, and reshape how we live and interact with the world around us.
So for you, the listener, what's the takeaway? Maybe it's a newfound appreciation for those everyday materials.
Right, the ones we often take for granted.
Or maybe a spark of curiosity.
About the emerging technologies that are shaping our future.
Right.
And a sense of possibility for a more sustainable world.
This deep dive has certainly left me feeling inspired and hopeful.
Me too.
It's clear that we have a long way to go, but this journey towards a more sustainable future, it's filled with these innovations and dedicated individuals.
It is.
Who are pushing the boundaries of what's possible.
And as we've seen today, sometimes the most groundbreaking solutions come from the most unexpected places.
Who would have thought?
Right. That a simple microwave could be the key.
To unlocking a circular economy.
Exactly.
It's a reminder to stay curious, keep exploring, and never underestimate the power of human ingenuity. To find solutions to even the most complex challenges.
Couldn't have said it better myself.
Until next time, keep those minds open and those imaginations fired up.
And we'll see you
on our next deep dive.